Okay, so far up till now, you have explored the first derivative test. I didn't call it the first derivative test, but that's what it is. And that's where we're looking at a graph and determining the extrema, the relative max and the relative minimum. So we look at, first of all, is the slope equal to 0? If the slope is equal to 0, there is a possibility that there is a relative maximum or a relative minimum. Now, in order to determine if there is a min or a max, we then have to look at whether or not the derivative changes from negative to positive or positive to negative. If the derivative changes from negative to positive, then the function has a relative minimum. If the derivative changes from positive to negative, then the function has a relative maximum. So we looked at a graph like this. Here's a graph of f of x. And if we look at f of x, we can look at the slopes, and we'd say that the slopes are positive on that first interval from negative infinity to a, and then the slope is 0 here at a, which I already indicated in my table. The slopes are then negative from a to b, and then at b we have a slope of 0, and then after b the slopes change back to positive again. So we can say that the function is increasing, decreasing, increasing, which means that here at x equals a, we have a relative maximum. And at b, since the derivative changed from negative to positive, that means the function went from decreasing to increasing. At x equals b, there is a relative minimum. But there's an easier way. I mean, this table is fine and this table is great in some situations, but sometimes we can use the second derivative to determine if this function has a relative min or a relative max. So I want you to think about that for a minute. How can the second derivative tell you if there's a relative min or a relative max? Remember that the second derivative is measuring concavity, whether the function is concave up or concave down. I'm going to pause for a moment. I want you to pause this as well. And I want you to think about how the second derivative might be able to indicate whether there's a relative min or a max. Okay, welcome back. I hope you actually did this. If you notice at this first point at f of a, so here we know that the derivative is equal to 0. That's a really important part that must be true in order to determine if there's a min or a max. And then if we look at concavity, I notice here that in this region where we have a relative maximum, I notice that, oops, that's not the color I wanted, that this function is concave down. Okay, and then if I look at this region right here, b is a relative min, and what I can tell from the graph is that the function is concave up, and that is not coincidental. If the function is concave down on a region and there's a derivative that is equal to 0, then we can say that that point is a relative maximum because we know that the graph is concave down. And then similarly, if the function is concave up and at a point on that interval the slope is 0, we know that that point would be a relative minimum. So let's try one. Let me just create a function here that might be somewhat convenient. Let's see. Use the second derivative test to determine the relative extrema, mins or maxes, of f of x. Okay, so let's just look at an example. Let's say we've got this function right here that is Let's do x cubed minus 3x squared plus 4. So we've got this cubic function, and we're trying to determine relative extrema. In order to do that, let's first find the derivative. So we're going to find those critical numbers, the points where the derivative will equal 0. So those are our potential mins or potential maximums, potential extrema. So let's find the derivative. The derivative of this is 3x squared minus 6x. Okay, to determine where this slope is equal to 0, we'll factor this. If I factor out 3x, that gives me x minus 2. So I have two critical numbers. The two critical numbers, the values of x that will make the 0 are 0 and 2. So now let's determine the second derivative. Let's look at concavity. So if I find the derivative of that derivative up above, that will give me 6x minus 6. So what I'm curious about is, at those critical numbers, at the places where the slope is 0, is the function concave up or is the function concave down? So if I plug in, let's look at f double prime of 0. So let's plug in that first critical number, because we know the slope is 0 there already. Let's just determine concavity. If I plug 0 in for x, I get 6 times 0 minus 6. 6 times 0 is 0. 0 minus 6 is negative 6. So what this tells me is that the second derivative is negative, which means that f of x is concave down. Now I can say that x equals 0, we have a relative maximum. Let me write it a different way. I'm going to say relative maximum at, and I'm going to do 0 comma something. I'll find the y value in a moment, because it's a point. It's a place on the graph. So we need to find the x and the y. Okay, let's now test the other critical number. Let's test when x is equal to 2. So we have 6 times 2 minus 6. That's positive 6. We know that the second derivative is positive at that critical number, which tells me that f of x is concave up. And that tells me then that we have a relative minimum at the point 2 comma something. We need to find the y value. So I'm going to find the y value. I'm going to find f of 0 first. So that's 0 cubed minus 3 times 0 squared plus 4. So I know that f of 0 equals 4. That tells me that I have a relative maximum at the point 0 comma 4. Okay, now I'll find f of 2. If I plug 2 into the original function, I'm trying to find the y value. 2 cubed minus 3 times 2 squared plus 4. So 2 cubed is 8. 2 squared is 4. 4 times 3 is 12. Negative 12 plus 4 is negative 8 plus 8 is 0. So I know that f of 2 equals 0. So that means that the relative minimum occurs at the point 2 comma 0. This way works a lot of the time. There are instances, however, where if you do plug in the critical number to the second derivative, you could get an answer of 0. So if we say that f double prime of a critical number is equal to 0, that doesn't tell us whether the graph is concave up or graph is concave down. So what that means is that the second derivative test fails. We can't tell one way or the other based off of that. So what that means is you get to go back to the first derivative test. So you get to go back to using this table of values. We're going to be looking at negative infinity to positive infinity. We're going to be plugging values into the first derivative to determine whether the first derivative changes concavity or not. So if the second derivative fails, you get to go back to this first derivative test. So whatever the point is here, whatever point you're plugging in, you'll need to check the derivative on either side and determine then whether this is a relative min or a max. All right, that's it. This was a short one. Have a good day.